All right, so with that background, let's try to figure out, this is like your Jeopardy question. Here is your answer. What is your question? Okay, so the types of growth are described in terms of the direct or explicit formula. Let's try to figure out what kind of growth it is and what the rate or the fixed difference is. Right? So the question is, what are the recursive formulas? Find P2 and P10 of each. All right, so let's try to figure this out. Pn is 380 times 1.08 to the nth power. Now notice here, anytime you see an exponent, okay, anytime you see an exponent with a variable, that is a characteristic of exponential growth. Right. So here, this is the initial value, 380, whatever that is, maybe the number of bacteria at the beginning of an experiment or something, or number of patients of a certain disease at the beginning on day one or day zero. Okay, so this is exponential because of the exponent. See the word exponential has the word exponent in it. Growth at rate of 8%. Where did that come from? Well, because it's 1.08. All right, so that's what it is. The recursive formula here would look like this. Here, let me erase this. The recursive formula has to have P naught, which is the initial value. That's 380. And by the way, when you plug in 0 here for n, you have 1.08 to the 0th power, which is not 0. Any non-zero number raised to the 0th power, mathematically speaking, is 1. Okay, so 380 times 1, that's P naught, which is 380. And then to get P sub n, you take the previous number and multiply that by 1.08, because that's what you do in exponential growth, right? And then you can just plug that number in here. You have the explicit formula here, so you can find what P2 and P10 are. Okay. I will just do maybe just P10. Okay. Let's just not worry about this part here. All right. So what's P10? In this case, it's 380 times 1.08 to the 10th power, right? And you can just go ahead and calculate this. And you can take your calculator and you find that the P10, this is 10 units of time since P naught was 380, it turns out to be 820.35, okay, 39. You don't have to worry about rounding in general. If the context makes it clear, if it's a number of people, then you round off to the nearest whole number. And if it's a number of um, let's see, number of dollars or something, you can round to the nearest cent. Okay, but anyway, don't worry about the rounding for this class. All right, P sub n is 4,000 plus 300 n. Notice here there is no exponent, right? And so 300 times n, this is a characteristic of linear growth with a difference of 300 each time. This is very clearly written right there. All right. So here, the explicit, or sorry, the recursive, maybe I should write in different color here. The recursive number here, the recursive formula is P naught is equal to 4,000. Okay, because you can see that right here, when n is 0, P0 is 4,000. Just plug that into this formula. And then P sub n is P sub n minus 1 plus what? Remember, every time you are adding 300, so you take the previous number and add 300, that's how you get the new number P sub n. And now let's go ahead and try to find P10. All you have to do is really plug that number in here. So it's 4,000 plus 300 times 10. Remember, you do this part first. That's 3,000 added to 4,000 is equal to 7,000. Sorry that my numbers are going all the way to the end of the page. All right, so Pn is equal to 2 to the nth power. This is a special kind of growth. And of course, because this is in the exponent, it's an exponential growth. But more specifically, this is called doubling. You can see what it is, right? I think P0 is 2 to the 0th. Remember, I said any non-zero number raised to the 0th power is 1. P1 is 2 to the 1st, which is 2. P2 is 2 square, which is 4. P3 is 2 to the third power. And notice here, every time you are doubling the numbers here, right? 2 to the fourth is 16. And that's why this is called doubling. So all this is actually for this, okay? It's doubling. And look at the stories on the worksheet. On the worksheet, you will see a couple of questions, or maybe 2 or 3 questions on doubling formula. All right. Oh, by the way, for this one, we are not given, so we're not given the, well, I guess we are. P naught. We know what P naught is. That's one. We just calculate this, right? And then in order to find the nth one, you take the previous number and multiply that by 2, right? That's what we mean by doubling. And because 2 is actually, this is just 1 plus 1, and so it's 100% growth. And that's indeed what's happening here. Okay. You want to know what P10 is in this case? Yeah, what's P10? That's 2 to the 10th power, right? And you can quickly raise 2 to the 10th power, and you get 1024, all right? And you will see a problem that involves this number on your worksheet. All right, for the rest of this, I used to have a another example, but I wanted you to see how real and how serious this compound or compound interest, yes, including compound interest, how serious the exponential growth models are. And so, and we have a very good timely example. All right, it is called the coronavirus COVID-19 crisis. And these are some of the numbers I looked up from the CDC official site. They have recently changed some of these numbers because they keep making these adjustments. But these are pretty much the correct numbers. All right. So during the spring of 2020, as you know, the number of COVID-19 patients in the United States grew as follows. All right. March 1st, it may be hard to believe. March 1st of 2020, there were 30 known cases. 2 weeks later, okay, exactly 2 weeks later, and you may remember this day. That was a Sunday because the March 14th, the Pi Day, was a Saturday. I remember exactly where I was. And on March 15th, there were 3,471 cases. And then by the end of this is 2 weeks later. This is 2 weeks later. Okay. So 2 weeks from here to here, 2 weeks from here to here. And by the end of March, there were over 186,000 patients. And 2 weeks later, 2 weeks and one day later, there were over 600,000 patients. Okay. This, by the way, was exactly what the health experts had predicted. And the reason they knew that is because without any strategy to slow down the process, pretty much anything like the spread of the virus will grow exponentially. All right. And so based on the first 15 days of March, here's a question. The number T of, and by the way, here, T is the number of days since March 1st. Okay. So this is our initial condition. You can say P0 or P at time 0 was equal to 30. Okay. So based on the first 15 days of March, the number PT of infected people in the United States roughly followed the equation P of T is equal to, and this is the explicit formula describing this. You see that? Because instead of N, I'm using T because T represents time in general. Where T is equal to 0 corresponds to March 1st. All right, so T, what does T measure? T is the number of days since that day, March 1st. Okay, let's fill in the blanks below. Again, this is very timely and this is very real. Okay, so I don't want to take an excuse. I don't want to take anybody saying, look, all the math is boring and it just we never use that in life. This is life. Okay, I mean seriously, this is life or death, and so this is really, really important. And I think it's extremely important for just anybody living in this world to understand the difference between linear and exponential growth, especially the power of exponential growth. All right. I can't emphasize this enough. I'm going to repeat this over and over again in the coming days. Exponential growth is really important for you to understand. Okay. All right. So with that, let's go ahead and do some calculations. This 1.404 basically means 40.4% per day. You see how serious this is? This is how fast it was spreading for the first 2 weeks. And how do I know this? Well, here are the data. Okay. we didn't make this up. This is what we observed based on the number of positive cases in the United States for the first few weeks of starting on March 1st. All right, so March 1st, when t is equal to 0, now remember this pt is 30 times 1.401 to the tth power, all right? And so when t is equal to 0, of course, this is 30. All right, let me go ahead and write the whole thing down. 30 times 1.404 to the 0th power. Remember, this is just 1, as I said a few minutes ago. And so and then the actual data is 30. Okay. Now comments. This is the initial value. Initial value. Okay. So there. I mean, this whole model is set to this value. So there is no surprise that this is 30. All right. Now after 1 day, you multiply this by 1, all right, and the answer is you're gonna get 42. What's the answer to the all the problems of the world according to the Hitchhiker's Guide to the Galaxy? The answer is 42, right? Okay, actually there are 53. So we are a little off according to this model, which is based on the first 15 days, right? And so according to the CDC data, it's 53, but our model will show you 42. So if we were using this model from the very beginning, you know, you would say, yeah, there are about 40, there should be about 42 people on March 2nd, but there were actually more. On the third day, or actually when t is equal to 2, because there are 2 days from, you know, March 1st to March the 3rd, you do 1.414 square, and that's about 59. I'm rounding to the nearest whole number because we were talking about the number of patients. Okay. All right. So what happened to my thing here? All right. Actual data was much bigger at that point. Okay. But our calculation, according to the model, will say 59. And on March 15th, that's 14 days later. So you take 30 and then multiply that by 1.414 raised to the 14th power. Remember, you do this part first. Go ahead and calculate this on your calculator. I would strongly encourage you not just to keep watching this video, but get your calculator out and then try to follow the calculations by actually carrying on these on your calculator, right? The answer turns out to be 3,469, all right? Now the answer, the actual data that you see on the top here is 3,471. That's really close, right? Why is it so close? Well, that's because this model was based on these two values. Okay, so it's not surprising that this is the base of the model. All right, so the based in the model based on the first 2 weeks. Okay, now again, if you are a health expert, or if you are in charge of a local municipality like a city or village or something, and then you're listening to your health officials, and they are saying, look, we have tracked the numbers for the first 2 weeks, and here's a formula. Here's a formula we came up with, and now we can fairly easily predict what's going to happen to the number of positive cases. After 30 days, this will be what? What's 30 days after March 1st? That would be March 31st, of course, right? So imagine you are in the middle of March, and then somebody's asking you, okay, based on your model, how many more people will be sick, or how many more people will be testing positive in the next 2 weeks? Okay, in other words, what is the number of people who would be infected by the end of March? And you say, all right, that would be 30 times 1.414 to the 30th power. Remember, exponential growth grows fast. Yeah, so let me go ahead and write this in purple, because purple is supposed to be more scary. 790,924 people. And that would be your answer. Okay, if somebody says, look, if nobody takes precautions, and if we let this virus go free, how many people will be sick by the end of March? And you say, well, according to this model, we would have close to 800,000 people who would be sick with this. Now, that really didn't happen, okay? Because if you look at this data here, by the end of March, you had not 790,000 positive cases. You had only, sad to say only, but only 186,101 people, okay? And then if you were asked, how about the middle of April, okay? 45 days later, after March 1st, would be April 15th. On that day, how many people would be expected to test positive for the first 6 weeks starting on March 1st? And of course, you plug in 45 here, and this number is actually much, much higher. Right? So this will be 128.4 million Americans would be infected. That's more than 1/3 of the country. Okay, in case you don't know that. The actual data, right? This was not nearly as much as that. 632,548. Okay. Now I'm not going to become political, so don't worry about that. All right. But look at what's happening here. The actual data would have been much worse. Okay. So what I'm saying is, if this model continues to hold, which is based on the first 15 days of March, if nothing had been done by the middle of April, okay, more than 1/3 of the country would have tested positive. But in reality, that did not happen. Why? Okay. Well, it's easy, right? Because something happened right in the middle of March. Do you remember what happened? Yeah, I mean, the government, not the government, the entire country and some states basically shut down, right? And schools closed abruptly, and all kinds of measures were taken on that day or around that time. Gyms closed, the restaurants closed, and all those things. So the point here is that the actual numbers are much less. All right? And that's because some things happen to slow down the process. All right. So let me ask you this question here. If you, having noticed this exponential growth on March 2nd, all right, so here's what, let's say you're for some reason you're tracking this. Maybe you're the leader of your community or something, and you saw that on March 1st, there are 30 people. And by the way, I do remember personally some of my friends saying on March, the beginning of March, let's put this in context. We have hundreds of thousands of people who die with the flu every year, and we're talking about 30 cases. What's the big deal? Well, the experts knew this was a big deal because of what they saw overseas and because what they saw in the first few weeks of March, right? And it says, whoa, this is serious. Of course, people probably knew that before that. All right, so having noticed on this exponential growth on March 2nd, what would you have been told if you told everybody how many people would be infected by the end of March? Okay, so in other words, you say, all right, so on March 1st, you had 30 people. March 2nd, you had 42. March 3rd, you had 59. All right, so how about the end of the month? And if you said to your friends, oh yeah, by the end of the month, you'll have about 800,000 people, they may not believe you that on this, because we tend to think linearly, all right? And but the truth is, it was growing exponentially like this at 40% increase every day. And with that rate, by the end of March, you would have had 800,000 people who would be infected. All right, I'm going to write down this because I'm going to, here, let me go ahead and write down some things under this. All right, and so just hold on a second. All right, so these are questions of reflection, but again, if you, based on the data on March 2nd, if you had told your friends and family or your constituents that by the end of March you'll have over or close to 800,000 people who would be infected, they may just laugh at you. Say, yeah, right. I mean, look at this. We have numbers like 30, 42, 59. But if you understand exponential growth, you would have known that. Okay, and so and they will say, yeah, right. Okay, but you would know better, right? And that's the point of learning exponential growth in a class like this. All right, next question. On March 15th, you remember that day? That was a Sunday, March 15, 2020, with only about 3,500 people sick nationwide. That's not very many, okay? Some cities like Los Angeles, San Francisco was already in lockdown, and LA, and basically they came up with this partial lockdown. Basically, the governor of California, as well as the mayor of LA, says stay home. Remember, stay safe, stay safer, stay home. Was that a good idea? what if nothing had been done? And I have already answered the question, but if nothing had been done to slow down the process or slow down the spread of the virus, which without any strategy would have grown exponentially, by April 15th, about 130 million Americans would have tested positive. And a few days later, the entire country would have tested positive. And so you can argue, what would have happened. Well, it's hard to tell what would have happened, because what would have happened by definition is what didn't happen, right? But the consequence would have been dire. Was that a good idea? Was it a good idea to do partial lockdown? Again, the opinions differ, but based on these numbers, you can make your own conclusion. Did it work? Okay, again, based on these numbers, you can make your own conclusion. And by the way, by the end of May, the country had successfully bent the curve, right? Now, of course, we didn't know back then what would happen in summer months, like after your Memorial Day and after your Labor Day and so on. But at least the exponential growth, at least for the first stage, slowed down. Okay, now remember the idea, bending the curve. What does the word bending mean? Here's the word bending means. All right. So in calculus classes, we call this growth concave up growth. Right. Concave up means if you're driving on this road, you're steering to the left. Okay. But bending the curve means you slow down. See, here's what happened. The numbers continue to increase for a while. All right. But, and this is the number of new cases, continue to increase for a while. But then it started to go the other direction. If you're driving on this part here, you're steering to the left, and somewhere here, there's what we call a point of inflection. And that's when you start to steer to the right, okay? And here, you're steering to the right. Even though the numbers may be still increasing, the rate at which the numbers are increasing, or I should say that the rate at which the number is increasing is slowing down, even if the number continues to grow. You see the difference between the fact that it's growing and the fact that the growth is slowing down. Okay, so that is the point of bending the curve, and that's what they wanted to do. That's what they wanted people to do, and we successfully did bend the curve. Okay. We don't know what's going to happen in the future. But anyway, this could happen. And so we need to continue to be vigilant, right? So bending the curve refers to the graph turning the other way. The increased rate slows down while, and it did happen during May. Unfortunately, things did not continue to get better. And so we are seeing the subsequent surges. All right, so this is a summary of exponential growth. All right, okay, hold on a second. All right, so on your worksheet for lesson number 15, you'll see questions like the magic penny, which mysteriously doubles every day. You'll have a question on evangelism. What happens if a religious group grows by doubles every year in number, and so on. All right, and so the answers are many times very surprising, and that's what I want you to see. I want you to be surprised. All right, so make sure you work on these problems and understand the power and possibly the you have the fear of exponential growth. That's going to really help us understand many big questions that we are facing today, such as the spread of a new virus, climate change, food shortage, and other very important issues. And speaking of other important issues, what you see in the background here is this number E, which is the basis of what we call the exponential or the natural exponential growth. And this is a sculpture, a mathematics based or mathematics inspired sculpture, which you see on, I think, the campus of MIT in Massachusetts. And this is inspiring. Okay, just looking at this number, this is the number that, by the way, also appeared in the equation for the normal distribution, the bell-shaped curve. This number, more than any number, is probably the most important real number there is in my mind, this number basically holds the universe together. And you can read about it if you like. Look up the book called E, exactly this, all right? And the subtitle is The Story of a Number, all right? It's written for a general audience, so you can read and understand at least the big portions of it. All right, so with that, I will see you next time. We'll talk about logarithmic scales. All right, we'll talk to you later. Have a great week. Bye.